So we've been discussing pointer analysis and we looked at Anderson's algorithm. I'm going to generalize Anderson's algorithm by looking at more programming language constructs than the 4 constructs that we considered when we discussed Anderson's algorithm. So, for example, languages like C allow you to do pointer arithmetic. So you can do P equals Q plus I, where both P and Q may be pointers. What happens to the points to information and the points to graph in the presence of such pointer arithmetic? Or the program can contain an instruction of the form P equals ampersand Q pointer dot F. This is C syntax. So for example, if I was to draw this, then if Q is pointing here, then P could point anywhere within the object that Q points to, right? So that's what P equals Q plus I means. So for example, this distance here between Q and P could be I, or even P equals ampersand Q dot F. So if F was a field here, then ampersand Q dot F is basically a pointer to that field within this larger object that Q points to. And similarly, P equals ampersand AI. So if A is an array, then once again, this could be, this whole distance could be I into whatever is the element size. So for example, I into 4 or whatever. And so P is pointing to within Q. And in all these cases, notice that P is pointing to the same object as what Q is pointing to. So P is only pointing to within that, just the only difference is that P could potentially point to the middle of that object. And that also we are just going to consider that as saying that P is pointing to the same abstract object as Q. So when we say that P points to an abstract object, then we basically really mean that P points to either the beginning or the middle of that abstract object. And so all these instructions basically make sure that P is also pointing to the same abstract object that Q may have been pointing to before this instruction. Now, you may ask the question, what if there was an overflow, in which case P could point to outside of this object? Well, this kind of pointing beyond the size of the object is usually illegal or undefined in languages like C and higher level languages than C. And so if P points to outside the object pointed to by Q, then that is undefined behavior, and that is the case in which case the program is actually illegal. When I say illegal, it does not necessarily mean that the compiler throws an error, but overall it's the programmer's responsibility to ensure that this kind of situation never happens, which means through pointer arithmetic or through an address taken field or through an address taken element of an array, you cannot point beyond the boundary of an object to which the original pointer Q or A were pointing to. And so, assuming that this all, anything that kind of any such operation that allows the pointer P to point beyond the boundary of the object, then we can kind of safely say that P points within the object that Q or A pointed to at the beginning of the instruction or before the execution of that instruction. So, using that fact, we can just treat all these 3 different programming constructs as simple copies, which means P equals Q plus I is just treated as P equals Q, because after all, P is just going to point to within the object that Q points to. Similarly, P equals ampersand Q dot F, treated as P equals Q, once again because P is just going to point to within whatever Q is pointing to. And similarly, ampersand AI, treated as a copy. And doing this, these transfer functions for these kind of operations assume that pointers cannot go out of bounds, otherwise it's UB or undefined behavior. Now, I'm going to also discuss a little bit about field-sensitive analysis. So for higher level languages like Java or C# or other languages which do not allow pointer arithmetic, you could have code something which looks like this. For example, you could allocate a new variable. So I'm going to assume that this new keyword allows me to allocate a new location to memory object. So I use x equals new, and assuming the allocation site abstraction, let's say the allocation site was 1, then x will, because by virtue of this instruction, x can point to an abstract object 1, which represents all the objects that are allocated at allocation site 1. Now when I say x dot f equals new, now that's basically saying that, let's say x was pointing to some object, then inside that, if there was a field f, then that is now being updated. So that's being updated to point to whatever is being allocated at this instruction 2. And anything that's being allocated in instruction 2 in an allocation site abstraction can point to 2. So in other words, this field can point to 2. And in our analysis, we're just going, so this is just like saying that the contents of the object pointed to by X can point to whatever we are doing, and that's as good as saying that star X equals new. So the only difference between star X equals new and X pointed or F equals new is that in this case, in star X equals new, we were actually overwriting the entire object. Here we are only updating a field of that object, but in either case, there exists a pointer in that object that can potentially point to an object that is represented by abstract object 2. And so just treat such statements as star X, x pointer dot F is nothing but just treat it as star X when you are doing the points to transfer function. And so this becomes star X equals new. Similarly, if you do x dot G equals new, then x pointer dot G equals new, then it becomes star X equals new also. And the resulting points to graph for this using Anderson's algorithm would look something like this. So x points to 1 and 1, which is the object pointed to, allocated at 1, may point to objects allocated at site 2 or objects allocated at site 3. Okay, so this is the points to graph if we use a field insensitive analysis. So notice that in this analysis we are not considering the fact that, well, this address can only live in the field F and that address can only live in field G. So for example, if there was another field G here, then this can point to 3. But in this field insensitive analysis, we're just kind of approximating this whole thing as a single abstract object and saying that, hey, the contents of this whole thing can point to either 2 or 3. And that's what this resulting points to graph is giving us. And that's why it's called a field insensitive analysis, because we're not being sensitive to the fact that different pointers may be stored at different fields. Okay. So let's see what are the implications of that. So for example, if I do y equals x pointer dot G, once again, what I'm doing is I'm reading the contents of the object pointed to by X and storing them in Y. And that's as good as saying Y equals star X in our field insensitive analysis. So X was pointing to 1 and 1 could contain pointers to either 2 or 3 based on the field insensitive analysis we did in the previous slide. Then Y can now point to whatever 1 may point to. So Y may point to either 2 or 3. Now once again, because this is a field insensitive analysis, we are ignoring the fact that Y is only reading the field G and G could only contain an object of type 3. And so a more precise analysis should have told me that Y can only point to 3 and not to 2. But because I'm doing a field insensitive analysis, I'm getting an imprecision because of that. And so it basically says Y can point to either 2 or 3. So it turns out that you can do better, but for that you basically the language style system should not allow things like pointer arithmetic or address taken fields, because in the presence of pointer arithmetic and address taken fields, it becomes very hard to say that whether this pointer may point anywhere in the middle of the object or whether it may point to field F or whether it may point to field G. Because if I just say Q equals P plus I, then if I is not a compile time constant, then whether P could point to field F or G becomes very hard to say. But many languages like Java and C# do not allow such pointer arithmetic or do not allow address taken fields, in which case you can track the contents of each field of each abstract object separately. So you can say that the F field of abstract object 1 can point to 2 and the G field of abstract object 1 can point to 3, and that gives you more precise information. So for example, you can say that in the same example that we had is that x dot F equals new. So that means the F field in object allocated at site 1 can point to 2. And the G field of an object allocated at site 1 can point to an object allocated at site 3. So the way to represent this in a points to graph is to label these edges based on the fields. So the edge label identifies the field through which it may point. So for example, 1 may point to 2 through F, and it may point to 3 through G. But notice that through G, 1 may not point to 2. 1 may only point to, if G is dereferenced, then only 3 will be obtained, but not 2. And so this points to graph is more precise than the field insensitive analysis graph that we saw earlier. Now, let's see the implications. So for example, if I do y equals x dot g, then y is dereferencing, looking at the field g, the contents of the field g in the object pointed to by x. So the object pointed to by x is 1, and the field that's being dereferenced is g, so that's 3. And so y, based on this field sensitive analysis, can only point to 3, but not to 2. And so the field sensitive constraints differentiate based on the field names, because we know that the field g is being dereferenced. And so based on that, we can say that y is only pointing to 3 and not to 2. And this is a more precise analysis than the one that we saw earlier, which was a field insensitive analysis. But recall that a field sensitive analysis is only possible if in the absence of pointer arithmetic and address taken fields. Well, it is in general possible. It may be possible even in the presence of pointer arithmetic and address taken fields, but it will become more complex. So typically these kind of analysis would be easier and more practical to implement for languages which do not allow pointer arithmetic and address taken fields.